what we were doing. We argued that we know the ground state of the Heisenberg ferromagnet exactly, and it's a degenerate ground state with a total spin equal to Ls, where L is the number of lattice sites on which the model is defined, and S is the spin at each side. And it is
sir, are you writing something on the board?
Oh, you can't see it, is it?
Yeah.
I don't know why. Okay, let me adjust this. Okay, so this is what I wrote. Total spin is Ls, and the ground state is, so this is the total spin in the ground state, and this is the degeneracy, 2 Ls plus 1 for degenerate ground state. Then what we were trying to do is to look at excitations about the ground state, and to sort of briefly recap what we did last time. We said that we can think of excitations in quanta of spin lowering. So if all the spins are pointing in some up direction, Z direction, then if I lower one of these spins, so all of these have a Z equal to S, then I lower one of these to Sz equal to S minus 1 state. So excitations have to be quantized in these units. And so we were trying to develop a theory for these excitations. And so what we claimed was that we cannot directly have, so these excitations were bosonic. And so therefore we introduced boson annihilation and creation operators, AI dagger, with the usual commutation relation. But then we said that we cannot have S minus, the spin lowering, as simply equal to my boson creation operator, simply because then I will go beyond the allowed 2s number of bosons at a particular side, because I should not be allowed to lower the spin any further. So keeping that constraint in mind, we introduced what are called, I wrote somewhere last time, Holstein-Primakov transformations, which define the SI plus and SI minus operators in terms of the bosonic A and A dagger operators through these relations. And we introduced the momentum space, corresponding momentum space operators, BK and BK dagger, with the usual Fourier transform relations between the A's and B's. And so then we were trying to write SI plus and SI minus in terms of the B's, and these are what we got. SI plus and SI minus, and SIZ, which should be equal to the maximum allowed Z minus the number of bosons at that particular site. And so when we write this in terms of the B operators, so this is in terms of A operators, this is written in terms of B operators. And then when we carry through this this thing, so what we get is so this total is sum over I, this thing. So I get a delta function from here. So eventually I get this. So this AI dagger AI or these, so these are boson number operators, okay? All right. So with these tools, we'll now try to write the Hamiltonian in terms of these operators and see what we get. And as I said, the target here is to find out the spin wave dispersion relation. So if I have a spin wave of some particular wave number k, and we got a more physical sort of picture of what these spin waves are, we discussed that as well. So we want to derive what is the energy expression for a spin wave with wave number k. So, so that algebra will now do. All right. So here is where we start. And this we wrote in terms of and now I'll write S, X and S Y's in terms of S pluses and S minuses so that we get and then you manipulate this term. So eventually you will write this as, okay, now I'm introducing something. Did I? No, I did not. So basically, so I'll sum this over all sides. Let us call that J. And for each J, I'll sum over just the neighbors. So these deltas are the neighbors of J's. So I have this. So this is the ZZ part. And then I'll have some terms from these transverse parts. So this will give me you can work this out. So this is what we'll get. Okay. Now what will we do? We'll write this. So just I showed you earlier, we had written S Z, S pluses and S minuses in terms of the B operators. So we'll now write these terms in terms of the B operators, and then try to see what form we get. So first we work with this term, the ZZ interaction part, or let's see. Okay, let me write the whole thing first, and then we'll take term by term. So this thing was S minus. So this part comes from this is JZ. And with that, I have this is ZJ plus delta, which will give me how did I write this? All right, so these are these terms. Then I have the spin flip terms. Okay, so I'll write this term, and this will give me, something similar. You just have to keep track of the appropriate expressions for S plus and S minus. So I'll write this one. So this I write as e to the So this part is just Sj plus. You note that is either S plus or S minus is 1 minus A dagger A over 2S to the power half times either an A dagger or A. And we expanded that to the power half, and so we are writing the leading term here. And so we basically get two terms, one which involves one boson operator, the other which involves 3 boson operators. So this is this. And then we have to write, so this one we wrote for Sj plus, and then we have to write Sj plus delta minus. And summations are obvious. Here the sum, this sum and this sum, they go over all the k indices that you have there. So these two, this multiplied by this, gives you one of these terms, this term. Is J plus and is A plus delta minus. Similarly, you will have this term. So I'm not writing it again. So now, okay. So what are the kind of terms that we get? So now we'll look at the ZZ term first. And in all of this analysis, we'll keep terms only those terms which contain 2 boson operators. So we'll keep things like BK dagger, BK, and so on. We won't take terms that are this times this, because that will be 4 boson operator terms. So we are neglecting those terms. Those will go into this part of the Hamiltonian. But you realize from this, you see that you have 4 boson terms here. You will have 6 boson terms here, and so on. 4 boson terms from here and here, and so on. So those terms we are not looking at, right? I mean, we won't get into, but they exist. We are trying to get this part of the Hamiltonian. So this is the ground state energy, and this part with 2 boson operators, and we'll soon see that they turn out to be boson number operators. So basically that will give me the energy of the magnons. Okay, so we look at the ZZ term, which is this and this. So I'll erase this now. But just note that let us look at what are the sort of terms we get here. One we'll get is the S squared term from this and this. And then this multiplying this will get 2 boson term, this times this. Similarly, this times this will give me another 2 boson term. So apart from the J and the sum over delta, etc., let me just write this one. Okay, I'll straight away write this. All right. So I'll take this part is common, so I'll take that. So that is common to both terms, and then I'll be left with 1 plus so 1 delta, so E to the I K dot K dot delta. And okay, so this is this. Now, what I have here is, apart from the factor of J, I have a sum over J. Apart from a factor of capital J, I have a sum over this J. And for Ej, I have a sum over delta. So when I take the sum over J, so this sum over J here with the 1 over L factor will give me a delta function, okay, delta K1, K2. So one of the summations will go away and I'll be left with this sum over K and 1, and so this becomes a delta function. K1 is equal to K2, so that gives me factor of 1 and dk dagger dk. Okay, and then I'll have a sum over delta. Okay, so sum over delta will bring in the number of neighbors that each site has, which we called Z. So everything will get, you know, this whole thing will get multiplied by Z. And all right, what else? Now the Hamiltonian that we are writing, we have to, so if I do this, then I have to bring in a factor of half times J times sum over J, this thing. This half takes care of the double counting that I explained last time. So this part will give me what I had earlier. In fact, you can easily take, I mean, this is how we had got it. So this part, if we are starting from the completely polarized state, will give you the ground state energy. And we are focusing on this part. So this part will give you this part will give you mod of J Z S dk dagger dk. So E naught plus this. How do you get this? So when you take this factor of half here, so this 2 that you have here will get cancelled by this factor of 2 over here. You had a minus sign. J is negative for a ferromagnetic model. So you write mod J and put a plus sign here. Z comes from the sum over delta. And S is, of course, there was S here, this S. So this is what you get. Okay, so just considering the ZZ part of the Hamiltonian, we have something which is something multiplying the boson number. So that's just, sorry, there was a sum over K. Okay. This sum over K. So this time, so this gives me at least part of the energy. Okay, but now we have to consider the spin flip terms as well. So keep this in mind, and then we'll see what we get from the spin flip terms. Okay, so so we had two terms. One was is I plus is G minus, and the other one was is I minus is G plus. So if I call this the H naught plus minus, let's see what we get from this. There was a J by 2, you remember, and we bring in one additional factor of 2 in the denominator to take care of the double counting. And then I take S plus and S minus on the nearest neighbors. And then basically, if you look at the expression for S plus and S minus, I write only that much, which gives me a term involving two B operators, nothing more. So if you do that, we don't write the 4B operator or the 6B operator terms. So you'll only get this much. Okay. So then and I pull the RJ part here, and then along with that, I have e to the minus I k2 dot delta and is sum over delta. And then I have k2. Okay, so this 1 over L sum over J this part will give me a delta function. So one of the k sums will go away. I'm left with one k sum. So this eventually gives me minus. Now we define this quantity. So you define gamma k to be minus I t dot delta. So that's just a definition. You see this appears here. So I define that quantity gamma k. And so I write this in terms of gamma k. And I'll get mod j s z k bk bk dagger. So this is what we'll get from the plus minus term here, this one. As you see, I mean, as we sort of made the approximation, this is the term that involves two boson operators. Now, of course, I have to evaluate that term. So I want, it's exactly similar. I mean, I don't have to do it separately. You just put in S plus and S minus on the appropriate side, and you will find only the first term of S minus and the first term of S plus, which contain only one boson operators. So product of these two terms only contribute to this order. Okay, so what you will get is H naught, let's call that minus plus. That will turn out to be bk dagger bk. So now we have all the pieces. We have the piece we got from the ZZ part of the Hamiltonian. We got the part, this is the part from this, and this is the part from this. So we have to now add these three. Yeah, let's see. So apart from the ground state energy, what you get is, so this Hamiltonian to this approximation works out to be the ground state energy plus this is what we had got from the ZZ part. And now these two. So this one and then that one. Okay, so in this, what we'll do is we'll use the bosonic commutation relation to write that as, so two things we'll do here. One, we'll write bk dagger B1 plus BK dagger BK. So that we'll put here. The other thing we notice is that if the lattice, any lattice has inversion symmetry, right? So if we are considering this spin model on some lattice, then of course it has inversion symmetry. In that case, so let me write this as because of inversion symmetry, gamma minus K is equal to gamma K. And that is simply because if you have a lattice, I mean, what is gamma K? Gamma K was sum over delta e to the minus I K dot delta. For any given K, if I'm on this side, delta are the vectors from this side to the neighboring side. So if I have a vector like this, I also have a vector like this. If I have a vector like this, I also have a vector like that. So now if I change K to minus K, it doesn't matter because for K, whatever contribution this vector was given, now for minus K, this vector will give the same contribution. And when I sum all of them, I get the same thing. So because of inversion symmetry, I'll have this. Okay, now when you put all of these together, what you get is this. Okay, one more thing. So now this term is written as gamma K 1 minus BK dagger BK, and this term is written as gamma K BK dagger BK. Okay, so I'll get, there was a minus here. So 2 BK dagger BKs I get, you can see. But I'm also left with a term which is just gamma K with a sum over K. So what is that? So how to evaluate that? So this is just this. Gamma e to the minus I e dot delta, right? There was a 1 over z, but that's okay. So this goes as so if I pull the delta, this thing out, sum over K e to the minus I e dot delta. So this, apart from up to a factor of L, is equal to delta function of delta 0, right? Because when I'm summing over K, I'll get non-zero contribution only when this delta vector is the 0 vector. But that can never be because delta is a vector which connects any side to its nearest neighbors. So that is never a 0 vector. So this is always 0. So this first term, sum over K delta gamma K will give me 0. So now when you put all these pieces together, what you have is this. You write this as, so this 2 will cancel with, this 1 over 2 will cancel with these 2 and the 2 factor that you get to this term. And you have sum over K 1 minus gamma K BK dagger BK. And that you just define as some omega k bk dagger bk. Right. So this is number operator of bosons. So this gives you, this omega k gives you the energy of a magnon of wave number k, and which is this factor times 1 minus gamma k. So that's the energy of a magnon of wave number k. So how does it go? So we have found an explicit expression for the magnon energy in some approximation, and that approximation is that we have neglected terms which are more than boson number. So we have neglected 4b terms and 6b terms and so on. So let us see what is omega, how does it behave as k goes to 0. That's the long wavelength magnon. So I'll erase this part over here. So omega k, which goes as 1 minus gamma k. And as k goes to 0, so this goes as square minus k dot square by 2 and so on. So basically it goes as k squared. That's the point. As k goes to 0, this energy goes as k squared. So first thing to notice is that at k equal to 0, the energy is 0. So you have gapless excitations. These are the Goldstone modes that I mentioned last time. You get Goldstone modes because the ground state is a spontaneously broken symmetry phase. What is broken is the continuous spin rotational symmetry of the Hamiltonian. The Hamiltonian has a continuous spin rotational symmetry which is absent in the ground state. So that broken symmetry, spontaneously a broken symmetry, is manifests as existence of Goldstone modes, which are gapless excitation. So these are sort of the symmetry restoring modes. So that is one point, and the specific information here is that this energy goes to 0 as k goes to 0 as k squared. So that's an sort of added piece. Okay, so that's about magnons in ferromagnets. Just one concluding remark is that will this energy change if we did include the 4 the quadrilinear terms and the higher order terms in B? The answer is no. You don't have to sort of get into the full technicality of it, but just in case the question came to your mind, the answer is no, because of the particular structure, the particular way in those in a particular way those terms appear. If we were to write down those terms, they come in the form that bk. I'm writing the 4b term. So the exact way they appear is like this. So this is the kind of terms that you will get. So then what this means is that you are destroying 2 magnons of wave vectors K4 and K3 and creating two more magnons with wave vectors K1 and K2, but with this conservation. The sum over K is conserved. So the momentum is conserved. So basically, these are like magnon-magnon scattering processes. Two magnons scatter give you two other magnons. It doesn't really affect your energy. So these states, in fact, one can show are exact eigenstates of the Hamiltonian. That's the exercise we did actually from Ashcroft's book in a slightly simpler language. Here I'm trying to state it in a more sophisticated language. So this, whatever you get here, this energy, so when you have one magnon, the energy would be this plus this, and that's an exact eigenstate of the Hamiltonian. Another way of saying this is that because the magnon-magnon interaction is in the form of scattering with this conservation, when you have one magnon, there is nothing it gets scattered from. So therefore, that just persists in the system, and that's an exact eigenstate of the Hamiltonian. How can you use this sort of formalism? Where is it useful? Well, you know what the energy of a magnon is. So therefore, and these are excitations above the ground state. So you can ask how many of these, how many of these magnons of a particular wave number would be excited at a given temperature. You can do the statistical mechanics of it, and from that you can calculate. You know, excitation of magnons lowers your magnetization that we saw last time. If you look at last lecture's notes, the total got lowered by the magnon number AI dagger AI. So therefore, if you can calculate average of these quantities, you can calculate at a given temperature how much the magnetization will be lowered by thermal excitations of these magnons. So that is something, again, I'll give you in the next assignment to work out. Okay, so I think that's all I wanted to say about ferromagnetic Heisenberg model. If you have any questions at this point, you can ask me. I'll give you a minute. Okay, if not, let us close the discussion here. And we'll go to the discussion of Heisenberg antiferromagnet. The Hamiltonian is written in the same form. Except that now J is greater than 0. Again, we are considering only nearest neighbor interactions. It need not be so, but that's the simplest case you can have. Okay, so we have already worked this out. So I'll straight away write this in this form. Okay. So one of the first things we did for the ferromagnetic model is to ask whether we can identify the ground state. So let's try to do the same thing for the Heisenberg antiferromagnet. I have already sort of mentioned this, that so what we did there in the ferromagnetic case is to try and optimize the pair interactions, minimize energy corresponding to pair interactions. Now, what we said is that if we are on, this cannot be done even if the system is an antiferromagnet. So, for example, if I have, it's difficult for me to, so what I'm trying to draw is a triangular lattice. So I'll crudely draw it. Oops. This, and so on. So this is sort of, this will give you, no, I'm making a mistake. That's why. So, okay, so this is a honeycomb lattice, as you can see. But if you also have lattice points inside this, then you have a triangular lattice. And if you are on a triangular lattice, and suppose you have a spin here, let's say this is up, how many neighbors does it have? Six. So for me, it is easiest to give you an example. I'm not able to draw the lattice correctly, but suppose the environment is such that you have, I'll try to come up with a lattice picture next time. But the point I was trying to make is, suppose this spin has 3 neighbors and the interaction is antiferromagnetic. So you know how to put this spin, but this one you don't know. So up and down are the same thing. So in such lattices, you will have what are called magnetic frustration. So we don't want to consider this. This is a completely, I mean, this is a sort of separate direction. So we don't want to get into this. We are interested in simple antiferromagnets where there are no frustrations. So therefore, we'll consider only lattices on which there are no frustrations. So a simple case would be, if you think of the simplest thing you can think of, either a monatomic chain in 1D or a square lattice in 2D, even a honeycomb lattice there's no frustration on the honeycomb lattice. So in this square lattice, I can alternately put spins as up and down. And I can continue this indefinitely and on all sides infinitely. So there are no problems. All bonds can be optimized, bond energies up and down. So such systems are called, this is a term that useful to remember, bipartite lattices. What are bipartite lattices? You divide the lattice sites into two sort of groups. Let's say I call one of them as up, the other as down, or the one as A, the other as B. This one is A, this one is B, this one is B, this one is A, and so on. So that all A sublattice, so A is sublattice, A is a sublattice, B is a sublattice. All sites on the A sublattice has only B sublattice points as neighbors. All sites on the B sublattice has A sublattice sites as neighbors. If you can divide your lattice in that fashion, then that lattice is called a bipartite lattice. And if you are on a bipartite lattice, you can put all spins as up on one sublattice, all spins as down on another sublattice without any frustration. So we will be focusing only on bipartite lattices. Okay, so that was my point. Okay, so there are no issues about frustration. So we only have bipartite lattices. So in that, let us try to minimize in such a bipartite lattice. Let us try to minimize a particular bond energy, some EIG. Okay, so EIJ, how would I write that? So we had derived this earlier in the case of ferromagnet. So I'll write that expression once again. You can go back to it, except now that the sign of J is different. So how can I minimize this? I can minimize this by minimizing this. This is for spin-S Heisenberg model. This is a sort of given number, and the minimum value of Si plus Sj squared is of course 0. So this is the minimum. Okay, then what is the argument? This is good. But the point is, can we minimize this bond energy by putting them as up and down? So in the ferromagnet, when we put the two spins as both as SS and SS, that minimizes the energy. In the antiferromagnet, if I put these two spins as this, does that minimize the bond energy? Is this the same as this? Let us see. So when we have this state, what we get? So there are two parts to the Hamiltonian, the ZZ part and this part. So when SI Z dot HGZ acts on such a state, so this is a product state, remember. Minus, so I'll get Z as S from this, minus S from this, S squared, and S I S minus S J. That is good. However, I have terms like this. So what would they do? So this one would give me 0 because Sj is already minus S. I cannot lower it any further. So this term will give me 0. But when I operate this term, so when Si minus Sj plus, when this operates on this, I'll get, apart from factors, I'm not writing the factors. The important point to note is that this spin will be raised, this spin will be lowered. So I'll get S minus 1 here, S minus S plus 1 here. So what is the message here? The message is that the S minus S state is not even an eigenstate of the Hamiltonian. That's the important thing to realize. It's not even an eigenstate of the antiferromagnetic Hamiltonian. Forget about it being the ground state. It's not even an eigenstate. So therefore, things are not as simple or as straightforward as in the case of ferromagnet, where just taking the maximally polarized state, one could say that this is the ground state, or at least one of the ground state among many, of the set of degenerate states. Here, this is not even the ground state. The up-down state is not even the ground state. So this is a very crucial point to understand about antiferromagnets. Okay, why is that? Now, because the up-down configuration lowers the energy of the Z-Z interaction part, but then you have the spin flip part. And as far as that part is concerned, this is not the best configuration. On the other hand, if you construct the singlet state out of two spins, and again, this is something I'll ask you to work out. If you write down the singlet state of these two spins, you will find that that has a lower energy, and that's in fact an eigenstate of the Hamiltonian. So it's the singlet which is the ground state, not just the up-down state. Okay. Okay, then what is the argument here? Next sort of step of the argument. So what I want to convey from here is that this is not the ground state of the antiferromagnet. For two spins, it's easy to see. You construct the singlet, which means you have to add another term, which is down up, and take the sort of, linear combination of these two, up, down, and down, up, with a phase of -1, and that will give you the lowest energy state. So it's the singlet, which is the lowest energy state. For two spins, it is straightforward to see. When you have spins on a lattice with L sides, you don't know how to construct the singlet. Okay, you don't know how to write down explicitly the singlet formed from L spin-S objects. Okay, but that's another complication. So, so again, but this was okay. So basically what we are now claiming is that, so for two spins, this was this much. This was exact result, by the way. This is exact. So this is the ground state energy of two spins. And so for the AFM on a lattice, so what we say is that this has to be greater than sum over EIG minimum and when you do that sum on this, what you get is J Z S 2 S plus 1. So the ground state energy is greater than this. Okay, so what we have found here is a bound on the ground state energy. The ground state energy has to be greater than this much. Let us try to look at it in another way. We consider this lattice. Suppose this is the site J I'm thinking about, and it has certain number of neighbors. Okay. So I have to erase some part. Let's see. Okay, so rather than trying to minimize each bond energy, we now try to minimize or ask what could be the minimum energy of interaction of spin on each site with its neighbors. So we focus on the site J, and Hamiltonian for the spin on site J is written as Sj dot sum over delta. Yes, delta, where delta of course goes over the nearest neighbors. Yeah, so that's that. And so we are trying to minimize this. So this we write as, this can be written as, so now we see this as a spin. So basically the vector sum of spins on the nearest neighbor sites of site J. Now viewing it that way, I can write this as this comes from simply Sj squared. Sj squared, Sj is a spin-S object, so Sj squared is S times S plus 1. So now we are viewing this as a single object, and the question is, so how do we, so the question one is asking here is, what combination of the spins on the neighboring sites? See, if I have a certain number of neighbors, each with spin S, there are several possible values that it can take, that combined object. So which value will minimize this energy? That is the question one is asking. So the energy will be minimized when this is maximized and this term is minimized. Okay. So we want to maximize this thing, and that is maximized when this takes its maximum value, which is Zs. You are adding Z spin-S objects, so the maximum value that they can take is Zs. So this will be maximized when the spin is maximized, and the maximum of square of that is this. And the minimum of this again is is G. Now this is maximized. So with that, the minimum value that can take, minimum value this can take is Z minus. So ZS is this, which is maximized, and then when the minimum of that will be Z minus 1F. So then you have to take the square of that and put there. So when you do that, what you get is, so these two combined from here will give you EJ, the corresponding energy, or EJ0 if we write it that way. If you work out the algebra, you will get Z squared 1. Now what we do? We sum over, we have to sum over all these sides, but then the exercise at different sides are not independent, because when you are talking about this spin and maximizing its interaction with this, and this, and then when you come here, you will again have to consider this, and this. So these clusters, if we think of clusters, so when I'm calculating energy corresponding to this spin, so there is a sort of, on this lattice, there is a 5-spin cluster that we have to consider. Similarly, for this one, and there are overlaps over these clusters. So it's not clear that you can simultaneously minimize all the cluster interactions. So the best we can write is, so from this, we can write is greater than when we sum over these interactions. Again, to take care of double counting, what we'll have is there's a J and L. So sum over J on this will give me L, Z, S. 1 by 2 will take care of the double counting times S plus 1 over Z. So there are two ways of looking at it. One way is sort of trying to minimize each bond energy. The other way is to sort of minimize energy of interaction of each spin with its nearest neighbors. This one actually gives you a lower bound, as you can see. This is an improvement over this. So the first term is the same in both cases. In the second term, here is 1 over Z, and here it is 1, because Z is greater than 1 in any lattice. So this gives you a lower bound of sort of a lower value of the bound on this thing. But none of these actually tells you how to calculate the ground state energy or how to construct the ground state for this antiferromagnetic spin system. Okay, so that is something to sort of keep in mind about antiferromagnets. What next do I want to talk about? I'll briefly talk about spin waves, spin waves in antiferromagnets, and point out a very, very crucial difference between how you should view spin waves in ferromagnets versus how you should view spin waves in antiferromagnets. Okay. So ferromagnets, we have already discussed in detail that you know the exact ground state, and these spin waves are collective finite excitations above this ground state. And they will lower your magnetization. That is the expectation value of Hz total. For the antiferromagnet, the problem is I don't even know the exact ground state. And what this tells me is that this classical state on a lattice, this classical state where I view this as, this is equal to Hz equal to S, this is Hz equal to minus S minus S, and so on. This state is not even an eigenstate of the Hamiltonian. So what one does is one still constructs a spin wave theory above this state. This is sometimes called the, let me write here, the classical ground state, or better still, it's called the nail state. One constructs spin wave theory about this nail state, but this spin wave in antiferromagnets do not give you excitations above the ground state, because the nail state is not the ground state, it's not even an eigenstate. What instead these spin waves give you is, it allows you to estimate how the magnetization is lowered. I'll come in a minute to what is magnetization in an antiferromagnet. So it allows you to calculate how the magnetization is lowered compared to this nail state because of these spin waves. So the spin waves in antiferromagnets should be viewed as, so let me write a few lines here to sort of make clear what I'm trying to say. So ferromagnets spin waves are excitation above the ground state. In an antiferromagnet, we don't know the ground state. Nail state is not an eigenstate. So spin waves, the theory constructed, gives so these are quantum fluctuations about the nail state. Okay, these are not excitations about the ground state, but rather these are seen as quantum fluctuations about the classical ground state, which is the nail state. And so this allows you to calculate how much I'll come to this, staggered magnetization is lowered these because of quantum fluctuations. So these are quantum fluctuations because we don't know the exact ground state. We have constructed some state and the spin waves are quantum fluctuations about that state, which sort of lowers this magnetization, or what is called staggered magnetization in a spin in an antiferromagnet. So I'll leave it at that because the theory of spin waves in antiferromagnets is mathematically a little more complicated because you have a two sublattice structure here. So this this creation annihilation operators that we were single operators for ferromagnet will now have to be you have to have two operators for two sublattices. So this gives a whole 2x2 structure to the theory. So we won't get into that. Just I'll leave. Instead, what I'll talk about a little bit is, I'll come back to this probably in the next lecture, is what is called the staggered magnetization. So what is staggered magnetization? What is magnetization? You have learned these things in your earlier classes, I'm sure. So magnetization you typically define by magnetic moment per volume or something like that. The volume is not important. I mean, you have to sort of normalize it by something. So you talk about volume. On this kind of models, it's not much point talking about volume. For real materials, you talk about per volume, unit volume. But on such kind of model system, there's not much point talking about volume. So one can talk about per site. So what is the magnetic moment per site? So when I'm in a ferromagnet, in the ground state, all spins are in SS state. So the magnetization, at least at zero in the ground state, zero temperature, the magnetization. So the magnetization is sort of defined as on this model is just this object. Okay, and in the ground state, this is just S because all spins are aligned. So that's S. In an antiferromagnet, because I have equal number of up and down spins, this will always be zero. So it's a useless quantity. It doesn't tell me anything about magnetic order in the system. It will always be zero, even in the this, at least this classically ordered state, it is zero. So how can we define something more meaningful? Well, we can define something which is, we'll call this is or let me put it this way, average of sum of so assuming that I define spins, I put up spins on A sublattice and down spins on B sublattice. So when I take SZ for the B sublattice, I multiply with a minus sign so that these two will come with the same sign. And when I take an average of these things, then I get a non-zero quantity, non-zero number, even in the antiferromagnetic state. So this thing is called the staggered magnetization. And that will give me a non-zero value in the ordered state. So this is what is staggered magnetization. And this spin wave theory allows you to calculate how much the staggered magnetization is lowered due to quantum fluctuations about the Néel state. Okay, so I think I'll leave the discussion of antiferromagnetic Heisenberg model here. I don't want to get into further technical complications of this. So the points to remember is that this up-down state is not the ground state. It's not even an eigenstate. For a two-side problem, you can explicitly show that the singlet state is the ground state, which I'll ask you to work out. And and you should remember what this staggered magnetization is. Well, anything else? I mean, any question you have at this point?
Sir, I will ask questions in the next class.
Sure.
Now, I have to read the things and do it myself first.
Yes. It takes a while to sort of digest the ideas of spin wave excitations. I would suggest that you first read whatever I discussed in the beginning in the last lecture from Ashcroft's book. That gives you a very simple physical picture. And this part is from Fazekas's book. It's a little more mathematically elaborate. Once you understand the simple physical picture, this takes you a step further. And there also we haven't discussed, of course, all that is there in Fazekas's book, but only the essential, the basic ideas. Okay, in the next lecture, what I'll try to do is give you some sort of phenomenological notion